All right, time to play with larger amount of data. This is part 6 of Build Your Own SQLite challenge. In this one, we need to retrieve data using a full table scan. So far, we've done all of these. Print number of tables, find names of tables, count rows in a table, fetch data from single column, multiple columns, then process where clause. And now we're down to this. This is stage 7, right? So let's see. Let's figure out what this is. In this stage, you'll deal with the same syntax as before, a query with a where clause. However, this time the table you'll be querying will be larger and it will span multiple pages. Okay. Here is how the tester will execute your program. So some database name and then a query, select ID name from superheroes. The eye color is pink eyes, all right? And here's the output it expects. So ID and the name. This ID, I think this one is going to be a slight bit, well, it won't be difficult. Oh, if you remember in our last video, we implemented the way to fetch ID alongside the table data, and we'll use that. We'll see. The tester is going to use sample database of superheroes that is approximately 1 MB in size. You can download small version of this to test locally. Read the sample database section in README. You'll need to traverse a B tree in this stage. If you're unfamiliar with how B trees work or just need a refresher, Vaidehi Joshi is busying oneself with B trees is a good place to start. For specifics on how SQLite stores B trees on disk, read the B tree pages documentation section. All right. So looks pretty straightforward. At this point, we understand the database file structure, how everything arranged, pages, page header, cells, cell header, and all of that. We also know, well, I think let's just jump to database file format and pages, I think. Yeah. So we know that there are two kinds of pages. One is your leaf page and the other one is your interior page. Then there are some, I'm trying to find. Okay, this. A table B tree interior page, a table B tree leaf page, an index B tree interior page, an index B tree leaf page. So far, we have not, we don't know the behavior of these pages, the arrangement, the structure of these pages. And we've been dealing with just the table B tree pages. And even at that, we've been dealing with only the leaf page, really. And now we also need to worry about this interior page, right? Because the data is split, and so we need to jump from page to page, fetch the data, and show the results. Okay, and we also know that there is some difference between the page headers and cell format in these two pages. I think let's just... Yeah, so this is B tree page header format, and I think the difference is that one of these values, I think the 4-byte page number is at offset 8 is the rightmost pointer. This value appears in the header of interior B tree pages only and is omitted from all the pages. All right, so this is one. And it says interior B tree pages, not necessarily table or index page, but all interior pages. So that is our 2 and 5. So if our page type is 2 or 5, then that means we'll have this value in our header. Then the format of a cell depends on which kind of B tree page the cell appears on. And this is the table of the format. So if we have a table B tree leaf cell, then table B tree is our page type and if you have a cell on that page. Then the variant, there is a variant which is the total number of bytes in the payload. Then there is another variant that is a row ID. Then our payload and a pointer to overflow page if our payload cannot fit in this cell, right? And this value is only available if the data is larger than what we can fit in a cell. Then we have our, again, B-tree table, interior B-tree table, and the cell on that. And the structure of this cell is, well, there are only two things: a 4-byte big Indian page number, which is the left child pointer, and a variant, which is the integer key. So this key again is the same key, this row ID, a variant, which is the integer key, aka row ID, and that is the same thing. But this 4-byte big Indian page number, this is new. This and it also says page number, which is the left child pointer. So I think at this point, I'm assuming you have read a bit about B-tree, or you already know about B-trees. But the idea here, and it is mentioned in this documentation somewhere also. Let me see if I can find it. But the idea is that the idea is that this left child pointer says if you want the values for row ID that are less than or equal to this key, then you need to follow the pointer. Otherwise, you can just, if you want values that are larger than this key row ID, then you can go to the next one. So this is what the pointer says. And this is the same information, but in a different format and different structure. So this is our page 13 and page 5, and these are the two pages that we are interested in. This is 13 is our leaf page, and 5 is our interior page. And you can see on leaf page, we have a variant, that is number of bytes, then row ID, payload, and page number of first overflow page. On our interior page, we have only the page number of left child and the row ID, right? This is the information we have. Cool. And I think at this point, I believe this is sufficient information for us to make changes in our code and adopt to interior pages. But let's see. Let's first download the databases. Let's go ahead and do that. So we'll say download sample databases. Right. And now we have companies and superheroes. Let's see, let's take a look at one of those. So we have a table called superheroes. Let's say limit 10, and also turn the headers on. Cool. So we have, what do we have? ID, name, eye color, hair color, appearance count, first appearance year. Okay. All right. Cool. So I'm just going to go and execute our script, or I guess homegrown SQLite that we've been working on, and give it the superheroes.db and say tables. All right, so we can read tables. We have superheroes and SQLite sequence. Let's give it a query and see what blows up. Right. And what is this? main.py line 177 parse create table 131 parse create table. Oh, parse create table 131 this. So it did not find any matches. Parse create table, it is trying to parse the create table statement. Okay, let's see. We have create tables. Okay, there are double quotes. Right. Huh. All right. That's fine. That's okay. So we'll say there can be optional double quote and optional double quote, and same for this one. Right. Let's see. Okay. So this is now we are trying to parse a record, and it is blowing up on unhandled serial type 108. Yeah, so we also need to handle all of these serial types, because so far I've been just doing away with, I think, 2 or 3 of these. There is 12 serial type 1 and 0, and then this 13 is, I think, blob. String 12 is blob. Okay, so I think I'll just go ahead and implement all of these. 1 to 7 are just integers. Sorry, 1 to 6 are just integers. And then this one is float, and this is 0 if our schema format is 4 and higher. I think we are on 4. And this is 1 if, again, same condition per schema format. So let's just go ahead and do this. Let's say this content size is also 1, 2, 3, 4, 6, 8, 8. Okay, so it is not 1, 2, 3, 4, 5, 6. It's not linear, right? So let's create a dictionary, and we'll say one content type for 1 is 1. Actually, hold on, then we won't be able to denote these two. I think that's fine. We don't have to worry about including these two, 12 and 13 in this. But for now, we'll say for this um, 4 and then 6, 8, 8. Right. So 1, 2, 3, 4, 6, 8, 8. And then we have 8 and 9, and both content size are 0, the constant value. Sorry, 8 and 9. Right. So we'll use this table to convert our to read data based on the serial type, and we'll do that here. Right. So serial type greater than equal to 13 and odd, then we decode as text, and if serial type is greater than equals 12 and it is even, then I think it is just blob, right? Yeah, so we'll read n minus 12 by 2 bytes. So we'll say Um, right. So this is done, this is done. And now we are down to the, we'll say, else if serial type in our serial types, then we'll simply, actually these are mixed types. So there is also floating point number and there are these two. And I think we also have 0. Hang on, let me think. Okay, let's do this. Let's make this executable. Give it the stream, and it will return dot. I think read one and big Indian. We'll do the same thing for this and return none. Cool. Then we have 7. That is 64-bit floating point number. So we'll say, can you decode float like this? Only from hex. Yeah, I don't think that is possible. I think there is struct package. See, I think this one decodes bytes array. Struct.unpack format and string. Format, I need to look it up, but that essentially says big Indian or and 7 is 8 bytes. Right, so something like this. Let me check. Okay, and let me check the documentation. Okay, so F for float and this for big Indian. Yep. Okay. Then we have 8 and 9. So 8 is simply integer 0 and 9 is 1. So we'll say that. 0 and 1. Right. So this is everything. So now if our serial type is in underscore serial types dictionary, then we'll simply return serial type, and give it the stream. Cool. So that should take care of everything, all of this. We don't need to come back to this now. Let's see, what else? So unhandled serial type 108 is taken care of. Now we have unhandled serial type 11. And I don't think 11 is supposed to be there because 11 says if you have this type, then something is wrong with your database, right? So that means, again, now we are down to reading garbage. And we are reading garbage because the table structure is not as we expected. We are expecting it to be a leaf table, a leaf page so far. That's what we are doing. So let's take care of that. And I think yeah, low table rows. This is where everything is happening. So we have page header, and if we check page header, we can say if page header dot page type is 13, then we have leaf page. If page header dot page type is, I think, 5, then we have an interior page. Right. Let's also say this just to make the editor happy. Okay, so now whatever we are doing in this function right now, we need to do all of that under this if condition. And then if our page type is 5, then we need to jump from page to page until we find a leaf page, and then we need to do all of this, right? Well, not this. I think this information is same for both of these pages. So let's just move that up here. Right. Then we have these values. Well, right. So this is going to be a recursive function because we'll jump from page to page until this condition is met, and then we'll execute this code and return the values. So let's do, actually let's create a new function. Load cell data, we'll call it that, right? It expects cell pointers, it expects db, and it expects number of columns, right? All of that. And now we can simply say if our page type is 13, then return load cell data, give it the database, give it the cell pointers, and give it the number of columns. Cool. What if the page type is not 13? What if the page type is 5? And actually, let's go ahead and handle the else clause also. We are not going to have any problem in our tests, but you know, it's good to know that the else clause will blow up if we see any other page type, if we see an index page, for example. So we'll say page type page header dot page type is not supported. Okay. So we know that from this page we need to call this from under this condition we need to call this function again until we find a leaf page, and then we'll return, right? So something like that will happen. And so now we have some cell pointers, and these cell pointers they don't contain any data. They contain then the page number and the row ID. Where is that again? Let me find that. Yeah, so this first 4 bytes are page number of left child, and then there is row ID. Right now, we are not going to worry about this left and right thing. We just don't care. We need to read everything. So we'll just go ahead and read everything. And we also don't care about row ID because we are not operating on row ID. We need this row ID because we need the actual ID column, and that apparently is an index. So we need to find that value separately. What I mean by that is this row ID is not stored along with our cell content. So that's why we need to read it separately, right? So now we have these cell pointers, and if our page type is 5, that means we need to read 4 bytes, that is a page number, and then we need to read a variant, that is a row ID. We'll store both of these. So we'll say for pointer in cell pointers, we'll seek to okay, so we need to seek to this position. And we know that our page numbers are indexed from 1. So we need to do something like this. Page number multiplied by self.page size minus self.page size. This is also same as subtracting 1 from page number and multiplying by page size, right? Yeah. Okay. So we'll do that here. We need to seek to page header dot page yeah, we don't have page number in our header. Header does not contain the page number. Page number comes from, so page number either comes from this or SQLite schema table, and there is this root page, that is 1, or we read that page number from database from an offset, and that is how we know it is a page number, right? So if we have our page number here, can't we just set that on our page header? And yep, that should be doable. We'll say page number is an integer, and our function parse from also takes page number and instance dot page number is page number, right? So now we have page number on our header. Let's go back to our mark. Where is it? This. So let's say page header dot page number -1 multiplied by pb dot page size plus the offset of our pointer. Right? So this much, this arithmetic will give us the offset to jump to for that page, and then we add this pointer to our page offset and jump to the cell position from there, right? So that is what's going on here. And now we read page is, we read 4 bytes, that is our page number, and then we have row ID. Row ID is a variant, right? Yeah, row ID is a variant. So we'll say parse variant db.handle. Cool. So we have a page and we have a row ID. This row ID actually is not useful at this time. Yeah, it is not useful because it is not telling us any particular row. It just says if you want anything that is less than or equal to this row ID, jump to this page. And then when we jump to that page, we'll find the actual data and the row IDs there. So now we need to jump to this page. Okay. db.handle.seek will jump to our page -1. Actually, I think I should create a function on our database class and do all of this arithmetic there. Yeah, I think I should do that. But let's just finish this one first, and then we'll do that. Then okay, so now we are at that page. So we need to parse the header for this page. We'll say child header is page header dot parse from our, yeah, it also takes page number, so we'll give it a page number, and then we'll give it our db dot handle, right? So we have a page header. And we need to call this function again for this page, whatever page we have. So we are expecting db and table name, and from that table name, this is the only usage. We are reading the page header. Actually, let's just give it the page header. Page header and remove this. So we don't care about table name, and that way here we can give it the page header also. But first we'll go and fix the usage for this, right? So we are giving it a table name. Instead of that, we'll give it db.page for table name, I think. Okay, so now let's see, what do we have? Load table rows, we'll give it a page header, and then page header, if the page type is 5, then we'll get to this, and then we'll find the next child page. For that, we'll find the child header, and we'll call our function. So we'll get some results from load table rows. We'll give it the database and child header and number of columns. That is what we are going to give it. And then we can't just return the results. We need to collect the results. So we'll say values.extend with this, right? And then return the values. I think that should work. Bunch of highlights, but I think all of those are protected member. Yeah. So now we'll say load cell data, cell pointer. Oh, so we need the page number Here also. Load cell data. We need some kind of page number because, oh, that is why it was working for our first page and not for the rest of the pages. Let me fix this usage. I think I found the other one, the answer to another question. Yeah, this is why it was working because the page size, page number for SQL schema table is always 1, and we're just assuming we're not doing all of this arithmetic there, and it was just working, and I was wondering why it is working for that one and not for our pages. Now I know. So load cell data, I will give it a page number. And now we need to do the same thing. So this will turn into page number minus 1 into page size plus cell pointers. Yeah, it is getting ugly. I think I'll refactor the code a little bit and move all of this arithmetic to our database class. Maybe add one or two functions like seek to page or seek offset or something like that. Let's just focus on this first. Right, so we have cell pointers and the load cell data is getting number of columns. So it is expecting database and page number is going to be our page header dot page number. Cool. And if our page type is 5, I hope it is 5. Yeah, it is 5. Then for each pointer, we jump to that offset and we read 4 bytes. That's the value of our page. So our page number is this, and then there is a row ID that says if you want values that are less than or equal to this row ID, then jump to this page. And we don't really care about this one right now. Then we jump to that page, find a child page, parse the child header, and load table rows. Call this function again. And again, if the page that we jump to here is an interior page, then we'll repeat the same logic and call the same function again. Now, of course, Python is going to have some problem with recursion, but I don't expect it to have like, I know, hundreds or thousands of intermediate pages, interior pages. So for now, I'm willing to take this risk, but we need to do something about it. Maybe convert this into a loop instead. Right. Let's run this, see what happens. Page type 0 is not supported. Of course it is not supported. Page type 0 is nothing. That's nonsense. Line 163. Oh. Line 163. This. Okay. 159. So, all right, that means we executed this function once at least, and then entered again, and then blew up. Okay. It is most likely again some problem with the offset. We are reading wrong data, seeking to wrong or something like that. But let's just do this. Let's print our page header. And also print our pointers, cell pointers. And of course, there is a 0 in our cell pointers. So cell pointer cannot be 0 because cell pointer is the position of a cell inside a page, and the page, I mean, you can say page offset 0, but that again is not valid because the page is going to have a header that is at least 8 bytes. So you can't say the content is available at page offset, at 0th offset inside that page. That does not make sense. Yet we have a 0. So what is going on? And our page type is 5. So that is also the only page that we have. So we have a page type 5, and then this is just garbage because we are not able to read anything. So that means this blew up on first attempt. Let's see. Load table rows. This is a load table rows tb.page for table name, and this is exactly the same that was happening before we moved this out of here. So that exact same thing was happening here. We are extracting page header db.page for table, that table, and now it is happening here. So I don't see any problem with this. Right, let's see. Open the database, read the database header, 100 bytes, then read the page header, and that page header turns out to be, well, that is going to be our first page for SQLite schema table, and then we find a page of interest for that table, whatever table that we are trying to operate on. Now we'll find that page number from this call, right? We extract all of that information in load header and load schema, and then this call essentially is giving us the page number for this table name, right? So let's say we get back page, I know, 4, right? Load table rows, and this is the page header for page 4. Number of cells, let's say 10. So now we have 10 pointers. And again, I'm just making things up, making the values up, not the logic, and just to keep things easy. Right, so let's say we have 10 values, 10 cell pointers. Then each of these cell pointer, since our page type is 5, these cell pointers are going to point to an offset within the page. Is this correct? So page header dot page number -1 multiplied by page size, and this is, then we add the pointer offset. Yeah, looks fine. And then we read 4 bytes. Yeah, so this actually looks like it looks like only the first value is garbage and everything else seems to be, I mean, I don't know for sure if these are correct values, but there is no 0 or negative value or some ridiculous number like, I know, 3,000,085 something. So we have a page number in our header, and this page number, we are not even calculating this. This is, we are just, oh, I think, yeah, this is the problem. So when we parse the header, we also need to parse this. Yeah, I think this is the problem. Anyways, even if that is not a problem, we need to do this because the header is going to be wrong size otherwise. It will be 12 bytes and we'll parse just 8 bytes. Yeah, I think this is the problem. So let's do this. And this value is only available if our page is interior B-tree page. So 2 and 5. So we'll say if page type in 2 and 5, then instance dot, I think that is the right pointer value. Yeah, rightmost pointer. We'll call it right pointer is, again, I think that is an integer 4 byte. Yeah, so we need to read an integer using 4 bytes. Right. And let's just also set that here. Otherwise, we don't have any right pointer. I think I don't need this else condition. It is actually I'm not sure if it is going to be none or 0. Let's just keep this. Let's see. I'm pretty sure that is the issue. Okay. So we have a bunch of stuff. Oh, so these are all our print statements. Is that these two? Okay, now there is an exception. The exception is line 213. Star is not in list. Table column dot index. Oh, so this star is not in list. Okay, that's fine. That's all right. Let's go to this. Let's just copy this whole thing. Oh. None type object has no attribute decode. Yeah, I think that is because of this ID column. Let's run this without ID because I don't think there is any other issue. Okay. None type object has no attribute decode. And the example for this is, result for this is line 111. Eye color. Okay, so eye color can be none also. I mean, any column value can be none. We need to handle that sensibly. If val is none and value is none, if val is none and value is none, then we want to keep the row. Otherwise, we'll do this. None type object has no attribute decode. Okay. Yeah, I was wrong there. If val is none, then if value is none, return flow. Otherwise, don't return anything. And if value is not none, but our value can be none. Hang on, I'm trying to optimize things and making it complicated. It is pretty simple. So this value can be none. If it is none and our value, the thing that we are trying to compare against, is not none, then it is not a match. So we'll return none. If this is also none and this is none, then we have a match and we'll return the row. Right? We'll say else return none. Right, so this is if the value is none. Otherwise, if the value is not none, else. Yeah, something like that. And we don't even need this. Select name from superheroes where eye color is pink. Does that give us anything in this database? There are results. Okay, so we screwed up our filter function. That means value is row column index, this column index. And if our value is none, you know what, it can be even simpler than that by simply doing this. If our value is none, then we'll return none. Otherwise, if value.decode is this value, then we'll return the row. Okay. I mean, I don't see. Okay, let's do this. Let's print rows and print rows. Yeah, so we have results, but our filter is not working. So if row column index dot decode UTF-8 is value, then return row. If row column index is none, return none. Still empty. Hmm. What is going on here? It's also printer filters. Oh, yeah, of course. Yeah, we can't just split on this. Actually, we can, but so let's see. What are the possible cases? A equals B, A equals BC, A equals B, something like that. Something like that. Something like that. Yeah, so this is not good. I mean, we can write a parser for this, but then that really is not the objective. Match filters than this, and I guess we can split on equal sign and then just assume it is always equal sign. And later on, if we need to implement more of these operators, then we'll have to, properly parse this whole thing, handle quotes, handle operators. It will become, I mean, at one point we'll have to write a robust SQL parser. That's that. Right now, I think I'm just going to use equal sign. We'll do that. And we're returning these filters. So these are our filters. And zero value. One is our operand, both of these. And instead of this, I'll just say equal. Should work. Eye color is not in list. Eye color space. Pink eye space. Yeah. Where is it? Parse create table. Oh, this one. Filters is okay. So we have some data. Now, there is still the matter of ID column. Hang on. Let me remove these print statements. We do have ID, the value of the ID column, but that is not part of our row. And if we try to use that, I think it will just blow up. Oh, it did not blow up. So instead, just print nil values. Let's see, what can we do? So these are our filters, these are our rows. To select is going to be, what if I print this? What do we get? 0 and 1. So we need to pick 0th and first. So for now, I think can we assume that the ID column is going to be on 0th position always, or whatever column is our row ID column, whatever index is our row ID column. So that thing can also change. I think at certain point, I think we'll just have to parse this SQL with more robust code instead of just doing something and praying. For now, though, I think we can cut some corners as we have done so far. Yeah, and I don't think there are any more corners to cut anymore. It's a circle. Though table rows. Load cell data. So this is a row ID, and then we have our parse record. Yeah, I think let's do that. We'll give it db dot underscore handle num columns, and then we have this record that is I know what that is. Let's print it. And let's break everything here. So we have none and then a bunch of stuff. And what if we give it our sample DB? None and a bunch of stuff. Yeah, okay. All right, I think we are fine. So I'll just say row ID. And let's also write a to-do. Right. Ideally, we want to find the index of the ID column, find if the ID column is the row ID, and substitute the value at. So we'll revisit this. We'll see if this works. Unpack requires a buffer of 4 bytes. Record parser line 23. Seven. Unpack requires a buffer of 4 bytes. Really not sure what that means. Okay, let me look it up. Hmm. Content size 8. I mean, I can see that the use of unpack is it seems to be the right choice. Hmm. And unpack also takes 4 bytes, so that is also correct. I mean, it is crying about the right thing. Apparently, unpack requires a buffer of 4 bytes, and we are giving it 8. And this says IEEE 754 64-bit floating point number. Now, I don't know if the specification has something to do with this. I can look it up, but let me just quickly read the struct.unpack documentation, and then we'll decide. Hmm. Yeah, I don't know. I mean, we have 8 bytes to work with, and it takes only 4. And I don't know what to do with the rest of the 4 bytes. For now, let's just try and return only the 8 bytes. Let's see if that works. Unhandled serial type 10. All right, but it was fine. Like, um, oh, yeah, I'm an idiot. Yeah, that's what. Int object has no attribute decode, and of course it does not. Like 231. So okay, we'll change that condition to only decode if we have a bytes array. 231, this one. Each dot decode if each is a byte array. I think it is bytes array, not bytes. Else just each. Sequence item 0, expected string instance, integer. Oh, yeah, there is more to be done. So we'll say values string each. Actually, let's do this one here, and then we can say this. Now all of this is each dot decode UTF-8 if, then that means this is not byte array, this is bytes. Yeah, cool, seems to be working. And the video is also very long, over an hour now. So let's just push this one, and then we'll check out retrieve data using an index. I think this one is going to be a bit difficult, but let's deal with this first. I think state 7. Yeah, 7. All right. So there is that. Now, retrieve data using an index. All right. Let's get back to this one in next video. All right.